Welcome back. This is Lecture 2, The Calendar, the New Fire Ceremony, and the 18 Feasts. This lecture covers 3 things. Number 1, the mechanics of the Aztec calendar. Consequently, I'm going to have to teach a little bit of history and a little bit of science, but don't worry, it's going to be super interesting and fun, and if you've never taken astronomy, you're going to learn a lot. In addition, this section also introduces how the Aztecs recorded solar years and Venus cycles. You're going to like that too. Number 2, it introduces the New Fire Ceremony, a very solemn one for the Aztecs, and the lecture closes with the 18 Feasts. Let's do it. Okay, Part 1, the mechanics of the Aztec calendar. Before I explain how the Aztec calendar works and show you that it's actually not that complicated to understand or dissimilar from other calendars in other parts of the world, I'd like for us to think about the concept of time, because that will help us to understand calendars on a more profound level. How do humans conceptualize or intellectualize its passage, or perceive the concept of time? We perceive it because we notice certain repeating cycles in nature that appear with some regularity. One of the first cycles we notice is that of day and night. We also notice changes in weather. Sometimes it is cold or hot or rainy. For thousands of years, humans have been aware of the passage of time also in relation to celestial bodies, including the waxing and waning of the moon, as well as the relationship that exists between the movements of the sun and its effect on not just the cycle of day and night, but also on the seasons. Which of these cycles we consider more important and how we conceptualize them is at the core of calendar making. To make calendars, humans have had to rely on the movement of celestial bodies because those cycles are very regular. On Earth, there are no cycles with which we could make accurate calendars and accurate prediction. For example, humans cannot use weather to measure the calendar because weather phenomena is highly unpredictable. And in fact, did you know that drought cannot be predicted? Neither could earthquakes, for example. However, there are places in the world that are so unique. For example, in ancient Egypt, in Africa, where the flood of the river Nile was so regular that to measure its flow and the passage of time, they built these vertical structures that you see here called Nilometers with markers on them that were placed inside pits, wells, or architectural structures. Those in charge of keeping track were able to accurately predict the Aket, a season in the farming year for ancient Egypt. This system from antiquity no longer exists because they built after the Egyptian Revolution of 1952 the Aswan Dam. Remarkably, ancient Egyptians were able to accurately measure the length of the year with the flooding of the Nile and these Nilometers. But it is extremely rare elsewhere in the world to find a system as reliable as the flood of the River Nile. Let's talk a little bit about astronomy. Now, astronomy is extremely complicated. So I'm going to be simplifying some concepts that are going to be crucial in understanding how the Aztecs created their calendar. Not everybody is as fortunate as the people of ancient Egypt to have had regular events in nature that help them to count the time. The rest of humanity has had to rely on the movements of celestial bodies, particularly the moon and the sun, to create calendars. The moon has formed the basis for our months and the sun for our years. As I will show you in a second, they also relied on planets and stars. Creating a calendar is an arduous endeavor and a cultural production. When your calendar counts time in relation to stars, those timelines are called sidereal. Let's start from the beginning. Since the dawn of time, humans have noticed that the biggest and brightest object in the nighttime sky would be the moon. They began to notice that the moon went through certain phases. And because this is one obvious cycle that early humans began noticing, many early calendars are lunar-based. And many calendars continue to be lunar-based, especially in the Middle East, for example. And the moon has a cycle, and it goes through the following phases. And here I provide a diagram for you on the right-hand side. So we start here and we go clockwise like that. Full moon, That means the surface that is visible from our perspective is completely lit. It's actually reflecting sunlight, but for now, let's just focus on the phases that we see. So we have, I'll say them in order, full moon, and then we'll gradually go into waxing gibbous, first quarter, waxing crescent, new moon, we don't see anything, waning crescent, last quarter, and waning gibbous. Now the sun can be a little more complicated. And the first movement that is very important that I'd like you to reflect upon would be the Earth rotates on its own axis. In this diagram here, the Earth is partially lit and partially in shadow. And that relates to the fact that the sun is casting its light on this part of the Earth. And that means that this part of the Earth is experiencing daytime and this part nighttime. And the reason why that occurs is because the Earth rotates on its imaginary axis, but these are not really there. This is made up by us so that we can study it. So the Earth rotates on its own axis, and as everybody knows, that takes 24 hours. And that is what causes the day and night. Now, the other movement that the Earth makes is that it moves around the sun in a somewhat elliptical shape here. So that's the orbit. And this is the Earth's revolution around the sun. The other thing I'd like you to notice is that the Earth is tilted at a 23.5 degree angle. And this is the 23.5 degree angle. And that tilt makes all the difference because that is what causes seasons. The seasons are not caused by how far away or how close we are. That's called aphelion. And seasons are not caused by how close we are to the sun or how far away we are. It has to do with this inclination, this tilt. Let's go over the Earth's revolution around the sun because that's very crucial. The basis of most calendars is a year, including for the Aztecs. And the Aztecs worship the sun. It's very important, obviously. And just like everybody else in the world trying to figure out time, they were basing it on things they could observe. Let's begin right here. So the rotation lasts 24 hours. Here's the tricky part. Our journey around the sun, most people have a tendency to think it's 365 days, but it's not. It's a little bit more. And so we cannot divide this day equally into 365 because we have a fraction of a day. If we count our year to be only 365 days, we are already behind every year. And so every decade and every century and every millennium, it will accumulate. So it's very significant. So that's the first thing. The second thing I'd like you to keep in mind is that this tilt is always pointing in the same direction. The Earth's axes are always pointing that way, as you can see. It doesn't wobble around. Maybe we will do that eventually in the faraway future. But for now, know that this orientation never changes. Before we go over revolution and the effects on seasons, let me show you another convention. We divide the globe in half at its latitude here. It's called the equator. And the upper part would be the northern hemisphere. And the bottom part will be the southern hemisphere. So that's the first thing. The other thing is that our journey around the sun is not 365 days. It's 365 days and close to 6 hours. To be exact, is 365 days, 5 hours, 48 minutes, and 45 seconds. And that's the tropical year. That means not sidereal, which has to do with in relation to the stars. So let's begin with June 20th, the summer solstice. Now, you see the northern hemisphere during the summer solstice is getting more direct sunlight, and consequently, in the northern hemisphere, it's the summertime, but not so in the southern hemisphere. In the southern hemisphere, they're experiencing the opposite. And then gradually, the Earth moves towards this position, and that's what we call autumnal equinox. And the autumnal equinox falls between September 22nd and 23rd, and equi means equal, and that is because, as you can see in this diagram, northern and southern hemisphere both are receiving equal amounts of light. However, in the winter solstice, things change. And now we're at the end, towards the end of December, and that's what we call the winter solstice. And as you can see, now it is the southern hemisphere that is getting the most amount of sunlight, and that's their longest day. They're the opposite of what went down in June. So because the tilt is that way, see, it makes perfect sense. The southern hemisphere is now getting more direct sunlight than the northern hemisphere. And that's why at this time in December, the southern hemisphere experiences more heat and it's warmer than the northern hemisphere. So whatever the southern hemisphere is having in the winter solstice, it's the opposite here and vice versa. And then 3 months later, you have an equinox. And the vernal equinox could fall anywhere from March 20th to the 21st because the equinoxes, both hemispheres are getting the same amount of light, you see. And here, everybody has the same. Okay? The other thing is that during the autumnal and vernal or spring equinox, day and night are of equal length because there's no tilt towards or away from the sun. So both hemispheres are receiving the same amount and intensity of light. One last thing I will say in this section on astronomy that I trust you will find useful just in general, but also when I discuss Venus cycles is this: the sun's position at sunrise. Let's say that we are going to measure the length of a year. So every day we are going to get up before sunrise and begin observing the sun's position at sunrise. You are facing east here because the sun rises in the east and sets in the west. Let's say we start keeping data starting March 20th during the spring equinox. The next day, on March 21st, we will notice that at sunrise, the sun position is drifting towards the left or towards the north. And it will increasingly do that until it reaches this point on June 20th, which is the summer solstice. As I showed you in the previous diagram, it's like June 20th to 22nd. And then we will notice that the sun is then beginning to rise every single day towards the right, to the southern direction, until it reaches this point again, which coincides with the equinox. And this would be September 22nd, the autumnal equinox. And then on September 23rd, when we get up to observe the sun's position at sunrise, we again notice that the sun is rising right of that position, and so moving towards the south until it reaches this position on December 21st, which is the winter solstice. And then on December 22nd and every subsequent day, we will notice that the sun's position at sunrise is again moving, this time towards the left or the north, until it reaches this position. And that is the tropical year. It measures the time it takes the sun to come back to this position, or the position that we used to begin measuring. In latitudes nearest to the equator, this movement is gradual. In the tropics, it's less dramatic than it is in the Arctic in the north or Antarctic in the south. At those points, this move is more dramatic. So the closer you are to the tropics, the change is more subtle. Mesoamerica is near the tropics. Here are a few examples of calendars begun in antiquity from different places. For example, here's a Persian contract featuring a date from the Hijri calendar, which is lunar-based because it's based on the Quran. And here are pages with dates from Chinese calendar dating from the 770s before the Common Era. It is a lunisolar calendar, meaning it takes into account both cycles, those from the moon and the sun. Many calendars do that. And then the Maya observed many cycles, but most definitely those by the sun and Venus. And here is Stela C from Quirigua, a classic Maya site. The stela features a king, or the Ahau. His name is Kakchilil Chakyopat. And I brought this specific example because it features two things. Number one, for our purposes, this date 11 August 3114 before the Common Era, which is the last creation according to the Maya. So they began their reckoning from this date. It's a little bit like the year 1 in the Gregorian calendar. And by the way, in the first lecture, I put a 0 for the birth of Christ. But 0 as a concept was unknown in Europe. The Maya Stela reminded me of the fact. We'll take this up later when I teach about the unit on science and also schools. I'll explain to you their knowledge of math. And India and the Maya region are the 2 places in the world where 0 as a placeholder and concept develops. We'll go over that later. And this Stela C also is one of the few monuments that features both hero twins, characters from the Popol Vuh, the Maya book of creation. Speaking of creation, both the Persian and Islamic calendars begin their reckoning in 622 of the Common Era, because that's when Prophet Muhammad migrated from Mecca to Medina, and that's the Hijra. Other than that, though, the Persian and Islamic calendars are not related. And also, this is a great example of the creativity of the classic Maya scribes. Some of these stelae are 4 meters tall. Look at this example from Stela E, also from Kiriwa. Absolutely impressive artworks. Currently, throughout the world, especially the Western world, we use the Gregorian calendar. And this calendar was established in 1582 in Catholic countries first. I'll tell you a little bit more about that next. And the Gregorian calendar is a revision of the Julian calendar. I'll say a word about it next too. And both of those calendars derive from the Roman calendar, which is a really complicated calendar and a very inexact one. And maybe it's so complicated because it took from various ancient traditions, including from the Middle East, especially the Hebrew calendar, which is a lunar calendar. And the Roman calendar began actually in March. And that is why September, which means 7th, became our 9th month. The months had the names of Roman gods like Martius, Aprilis, Maya, Juno, and then it begins using ordinal numbers. Quintilis for 5th, Sextilis for 6th, September for 7th, etc. And that is why September, which is the 9th month in both the Julian and the Gregorian, actually means 7. The Roman calendar did not have January or February. That was added when the Julian was established. And look at this, it has leftover or unlucky days. It had like a bunch of days, 61 days. Because the Roman calendar was so complicated and didn't really reflect what was happening in nature in terms of the astronomical movements, in 44 before the Common Era, Julius Caesar proposed a calendar that became known as the Julian calendar to replace the Roman one. And that was adopted in 45 before the Common Era. And then, I forgot to bolden this. In 325 of the Common Era, Constantine I, the emperor of the Roman Empire then, declared Christianity the empire's religion at the First Ecumenical Council of Nicaea. And that's when they recognized the Julian calendar as the official Catholic calendar. And Easter Sunday, and this is very significant, which commemorates Jesus's passion and resurrection, must be, this council stipulated, must be celebrated on the first Sunday after the first full moon after the spring equinox. So you can see it had to be very exact. But nevertheless, the Julian calendar actually overcorrected because every 4th year they added a day. But that is wrong because the tropical year is about 365 days, 5 hours, 48 minutes, and 45 seconds long. So it's not 365 days, nor 365 days and 6 hours. So that's why the Julian was so way off. And then the sidereal year is the time it takes the Earth to orbit the sun relative to the movement of other stars. So it's in relation to a fixed frame of reference, which is usually a planet or a star. So the sidereal year is 365 days, 6 hours, 9 minutes, and 9.76 seconds. So this is why I'm telling you that Keeping a calendar is an arduous enterprise. You and I go to the store and buy a calendar, or today we have electronics, our computers and cell phones, and all the electronic devices, they're just reset. But scientists are watching this every moment. And I'm not even going into the animalistic year. I alluded to this when I was talking about the tilt having everything to do with seasons and not to the upsides of a perihelion or aphelion. I just put it there for science buffs. Consequently, the Julian calendar was drifting away from the spring equinox year after year. And they knew that. Europeans knew that. It wasn't until 1582, several centuries later, when the Catholic Church under Pope Gregory XIII proposed to revise the calendar. And this is a bit humorous because it's like a really extreme example of procrastination. Because Catholic officials understood, they knew that they were way off. Their calendar was so inexact. Look at this chart I found online. It lists ancient calendars, including the time when each was introduced and their approximate error. It also has the average length of the year, because by now you have heard this about 10 times in this lecture that the year is not 365 days. And these are some of the most exact calendars, at least those that we know about. And look at the Persian calendar. Introduced in the second millennium before the Common Era, the approximate error is less than 1 second per year. In other words, it's 1 day in every 110,000 years. That's pretty impressive. In the Maya calendar, also introduced in the second millennium before the Common Era, the approximate error is about 13 seconds per year, or 1 day every 6,500 years. The Gregorian, as you now know, adopted in Catholic countries first in 1582, and the Gregorian is a pretty great calendar. Not as exact as these other ones, but look at the approximate error. It's only 27 seconds per year, or 1 day in 3,236 years. So we're drifting 27 seconds every year. Not to worry though, because scientists watching, analyzing, and telling us when to do adjustments. And the Julian, the approximate error is quite large, especially compared to the other ones. It's 11 minutes per year, or 1 day in 128 years. This calendar is significant because it's the one that was used in the West at the time of the conquest in the 1520s. And so I want you to think about the way that the Western calendars has influenced not only the way that ethnohistory was written in the early colonial period, because the Aztecs were heirs to an elite tradition in astronomy in Mesoamerica. Mesoamericans, unlike Europeans, boasted an ancient tradition in calendar making based on astronomical observations. Look what Alfonso Caso, in one of the most cited publications, his article titled Calendrical Systems of Central Mexico. Even though it was written in 1971, it continues to be influential. He writes, a single type of calendar or method of computing time was in use from very ancient times throughout Mesoamerica. Everywhere the basic essentials were the same, although variations occurred in each region. From the formative period of the Preclassic, this calendar was in use, appearing with a knowledge of writing and having the fundamental characteristics that will be explained later. And this is the opening paragraph, and that's what he explains in this article, the mechanics of the Aztec calendar. And look at what the Aztecs say in the Florentine Codex. The Aztecs say that their calendar was an ancient thing and that it dated, quote, from time immemorial, unquote, because the Aztecs begin to form their nation, as I said in lecture 1, in the 1320s. So the calendar was devised by ancestors of the Aztecs who willed it to them. Now, in 1582, Pope Gregory XIII proposed to revise this Julian calendar. And for that endeavor, he commissioned some of the most gifted mathematicians in Europe. For example, the Italian mathematician Alesius Lilius and the German Christopher Clavius, to come up with a mathematical formula to correct a Julian. And what these mathematicians came up with became the basis of the Gregorian calendar. I should just address also the fact that we have a tendency to believe all scientific inventions generally come from Renaissance Europe. But I must point out that the so-called scientific revolution, and I say so-called because, as I hope this lecture has shown, scientific discovery has been with humans since antiquity. It has never stopped. There wasn't really a scientific revolution. Scientific achievements had been steadily accomplished since antiquity. But what happens is that with the discovery of the so-called New World of the Americas, new ideas were flowing into Europe. And old ideas from the Middle East and ancient Greece were experiencing a rebirth in Europe, if you will. And ironically, the Catholic Church, they sought to control scientific discoveries in order to hold on to power. And a stark example of this is Galileo Galilei, who made great advances in astronomy. He's a disciple of Ptolemy and Copernicus before him. And Galileo Galilei proposed that the sun, not the earth, was at the center of the solar system. So the earth was not the center of the universe, as the Catholic Church stipulated or wanted everybody to believe. And there's many ideas that Galileo Galilei began to promote in earnest in Europe. And for those ideas, Galileo Galilei was punished and put on trial and in jail. Ironically, though, the Catholic Church was both suppressing, but as the example of the revision of the calendar shows, also had to support scientific advances, especially in astronomy and the calendar. Here's a 19th century rendition of the trial against Galileo Galilei on the persecution that the Holy Office subjected one of the greatest scientific minds Europe has given. And this produced the Gregorian calendar, which is the one that you and I used in the West today. And even though there's some 40 calendars in use today, the Gregorian is widely recognized throughout the Western world. Now, European astronomy owes much to science from Asia, where the fields of astronomy, physics, and mathematics was extremely advanced. For example, the Hindu-Arab numerals began in India and developed over centuries in India, the Middle East, and Africa. In 628 of the Common Era, for example, Brahmagupta formulated 0 as a number, and the decimal numbers that you see here became standard and diffused in the Middle East, China, and Africa. Romans in Europe rejected this system as they thought that these Roman numerals were superior. One thing that is important is that after the mathematicians came up with a formula to revise the Julian calendar, they had to drop 10 days to correct it. At the beginning in 1582, only France, Italy, Poland, Portugal, and Spain adopted the Gregorian calendar. And then the following year, Austria and Germany followed, and they also dropped 10 days. Hungary doesn't join that group until 1587. And then Prussia doesn't adopt it until 1610. It's not until the 1700s when Protestant Germany and Switzerland adopted the Gregorian. And look, by 1752, the United States, which was part of the UK at that time, Canada, and the UK adopted the Gregorian. But they waited so long that they had to drop 11 days, not 10. And as you can see, the longer you waited, the more days you had to drop. Religion played a huge part in this. Protestant countries were less inclined to follow what the Catholic Church was ordaining. And in 1872, 1873, Japan adopted the Gregorian, and they dropped 12 days also, followed by Bulgaria in 1916, Estonia and Russia in 1918, Greece in 1923, and Turkey is the last country to make the switch in 1927, and they had to drop 13 days. Adopting this new calendar was actually very difficult because not only did you have to drop days, but you have to follow Catholic dogma. And at the time, in the late 16th century, the Catholic Church was losing part of its hegemony in Europe because of the Protestant Reformation. So, were there two calendars in use from 1582 to 1927 in the West? Yes. So keep in mind that there is no perfect calendar, and it would take 300 years for most of the world to adopt the Gregorian and abandon the Julian calendar. And look at this painting, alluding to the 10 days that the UK had to drop when they adopted the Gregorian calendar in the 1700s. This is an oil on canvas by the English artist William Hogarth. Its title is An Election Entertainment from 1755. It features a scene inside a tavern. Hogarth is known for his satirical works, like this one. There's this black banner on the floor, and it says, "Give us our 11 days." And that relates to the calendar. When Europe was switching from the Julian to the Gregorian, apparently people were very resistant, particularly the Protestant countries. Hogarth is depicting the corruption of the British government at the time. And these are the Whigs who had, through ruse, stolen a parliamentary election that supposedly the Tory party had won. Here, this black banner on the floor, and it says, "Give us our 11 days," held by this wounded soldier, and this guy is actually pouring alcohol on his head. I understand from scholars that riots and protests were actually not about the calendar itself, even though there was some resistance. But there were many, many jokes about it. There was one guy who made a bet that he could dance without stop for 12 days straight. And people took the bet, and then he began dancing on the day before they established the calendar. And the next morning he stopped and went to collect his money because he said, "Well, the calendar says it's been 12 days." Anyway, I don't know how to tell that. I can't remember the name of the guy. But over here, Hogarth is showing celebration and mayhem and foolishness too, because like, what happened to this guy? And what is that lobster doing here? No, like maybe this lobster is the like, why is no one doing anything about this lobster, by the way? And they like, what's going down? Look, no, let's move on. This is no. Oh my God. Now we're ready to see how the Mesoamerican calendar works. The way that the Aztecs named the days in their calendar is as follows. They used 13 numbers in sequence and in this order. This is the convention that they had. When we get to the unit on school, I will show you how they denoted bigger numbers. For example, a banner was 20, 8,000 was a pouch. We'll go over that. But for now, most manuscripts use this convention. Look at this example right here. See, 13, 12, and like that. Alrighty. So 1 through 13 in order. And then you have 20 symbols. And these are depicted in a very naturalistic manner, meaning you're not thinking, what is this? It's not some abstract object. Except I would say for Allen, which is movement. And this one is actually a very conventional. We all know that's glyph for a building, and this is for house, and this is for flint. So the first thing I'll do is to go over the names of the symbols, and then I'll show you how to do permutations, because to name the days of the calendar, the Aztecs and all Mesoamericans used these 13 numbers combined with these symbols to name the names of their days. And the ordered pairs had to be permutations, meaning we go from 1 to the first symbol, and then 2 with the second symbol, 3 with the third symbol, and so on and so forth. So that's a permutation. So in other words, you cannot use this one, and then this day you want to use it with that one, and then you'll do the next day this one and that one. No. Order pairs these have to be in this specific order, and these have to be in this specific order. Let me tell you the names first, and then I'll show you how to do the permutations. So we go Acato. I'll say this is the Nahuatl for read. So then I'll say the name in Nahuatl, and then in the translation into English. Alrighty. Acato, reed. Ocelotl, jaguar. Cuautli, eagle. Coscacuautli, vulture. Allen, motion. Tecpatl, flint. Cuyahuitl, rain. Xochitl, flower. Cipactli, crocodile. Ehecatl, wind. Kali, house. Quetzalpalin, lizard. Coatl, serpent. Miquisitli, death. Masato, deer. Tochtli, rabbit. Atl, water. Isquintli, dog. Osomatli, monkey. Malinali, grass. So then the permutations would be, then I'll show you in the whole chart. I'm insane. I did like the whole permutation. I'll show you. So we go. I'll go over the first 20 day signs, okay? 1, reed. 2, jaguar. 3, eagle. 4, vulture. 5, olin. 6, flint. 7, rain. 8, flower. 9, crocodile. 10, wind. 11, house. 12, lizard. 13, serpent. And then you don't go 14, you go back to 1. That's what the Western permutation means. So 1, death. 2, deer. 3, rabbit. 4, water. 5, dog. 6, monkey. 7, grass. And that's how you would form them in perpetuity, as I'm about to show you. Oh, I forgot to put that these symbols are from the Codex Borbonicus, from the manuscript I just showed you. And I picked those because the monkey has a corn cob on its head. And I'm writing an article about this, so it's really awesome. So again, don't forget that they have to be in ordered, and those in math are called permutations. Before I show you the permutations and how they work, and all of this will become so much more clear after we go through the whole cycle in the chart I created just for you. So Tonalpowali will be the first 260 days, or the 260 cycle, which basically means count of the days, tonal days. And then the 365-day cycle, and we'll take up the issue about the leap year later, is called Xihuitl, which means turquoise, precious, not only for the Aztecs, but for all Mesoamericans. So Xihuitl. It also means herb, which was also very precious for them, for reasons I'll explain later. And then the Xiumolpili is the 52-year cycle. So 52 solar years will be Xiumolpili, and that has to do with the new fire ceremony. This meant that every 52 years, the cycle would reset. And I will explain to you with a chart because it will become super clear to you after that. And that's why I made the chart for you. So this was one of the most solemn ceremonies or celebrations that the Aztecs had, which they celebrated because the Tonalpowali had gone through its whole cycle and was reset again, as I will demonstrate in a minute. And then this one, Nemontemi, is useless days or nameless, but as you will see, it just basically has to do with the fact that the Aztecs had 18 festivals, each lasting 20 days, which the Spaniards told us that would be the equivalent of months. And in Spanish, it's veintena, a bundle of 20 days. And so if you multiply 18 times 20, that gives you 360. So this is actually 5. Oh, I forgot to put the number 5. Darn it. So that's 5. So 18 times 20 is 360. As you will see in a second, all of this will make sense. I probably should have gone after, but then it will be just self-explanatory. You'll see, I promise. Before I show you that permutations, I wanted to show you that we're going to study this next in the next lecture, because this very famous sunstone, look at how exquisite the shallow carvings are on this stone. And this is from the post-classic. This sunstone is depicting the 5 ages, or the 5 eras, the 5 creations of the Aztecs. And it's showing you here 4 naui, that means 4 movement. And this band over here has the 20-day symbols that we just went over. Look at that. This is movement. Can you recognize any other symbol? Here's a difficult one for house, crocodile. And again, I'm going to go over this on the lecture for creation, but because it has the calendar, I thought I would introduce you to this here. And over here, you see Xiucoatl, which are 2 serpents over here. This is the tail, and then it comes over here. And out of their heads emerge Xiuhtecuhtli, the god of fire. And this one is Tonatiuh, the sun god. And I also wanted to show you this in this unit because this has everything to do with the sun and the sun worship. And it's just like so full of glyphs, which we will study in greater detail in the next couple of lectures. Here's 13 reed, for example, and then you see, I don't know, maybe you should have fun finding where the calendar symbols are here. This is a really clever way of writing the current creation, the current era, and then the previous 4 creations. We'll go over that later. And here you can recognize flint. But try to pause it here and then see what you recognize from this stone. And this is just another example of how the manuscripts had day signs. As you can see here, this is a glyph for house, movement, death, snake, reed, flower, monkey, rain, deer, etc. So now we're going to go through the whole count. Now, as you will remember, we did the first 20 symbols. So first, I'm going to show you the Tonalpowali, which is the 260-day count. Then we're going to get to 365-day count, which is the Xiuhwitl. And then I'm going to show you the Xiuhmompili, the 52-year bundle. Okay? It's really cool. So stay tuned, please. So we began, as you will remember from the images, I cannot put the images here. Okay, so we go 1 reed, 2 jaguar, 3 eagle. We went over through the 20, and then you continue doing those permutations. And based on mathematics, if you multiply 13 times 20, you will get 260. And that's how the Tonalpowali gets made. And then so over here, these are 40 symbols. Yeah, 13 times 3 is 39 and 140. Yeah. So 40 times 6 is 240 and then 260. So this is the 260-day sign, but then I told you that they would continue with the permutations, and then you will continue, and something remarkable happens that can be explained with math, is that this will be day number 365. So the next day is 2 flint. And as you will see, these are called year bearers because based on math, these permutations will produce a system in which 4 of the 20 day signs will appear as the first day of every Xiuhwitl, of every cycle of 365 days. And the ones that repeat will be 1 reed, 2 flint, house, and rabbit, as we are going to see. So now you're clear that the 13 numbers and 20 symbols will yield 260 unique combinations, which you would continue in perpetuity to produce the year, the rest of the day names for the rest of the year. That system produces years in which it's very predictable what will become the name of the first day. So the Xiuhmompili, the 52-year cycle, will go like this. So we began in 1 reed. In our town, we began in 1 reed, let's say. Then you have all the 365 days here with the 13, again, with the 13 numbers and the 20-day combinations for the permutations. And then the next year will be 2 flint. And there will be 3 house, 4 rabbit, 5 reed, 6 flint, 7 house, 8 rabbit, until you get to 13. Okay? So each one of these 4 year bearers would have gone through 13 cycles, each one, to produce 13 times 52 is, 13 times 4 will be 52. Okay, let's do it. I made this thing, so I might as well show you now. So we go. First day, again, first day that we start counting 1 reed. So then we'll go here, 260, like I explained, and then you get to the first year. What do you think will be the next year? If you guessed 3 house, you would be correct. And there it is, 3 house, because you would have gone through the whole cycle. And then you continue the count, and the next one will be 4 rabbit. And there it is, 4 rabbit. And then 5 reed right here. and then 6 flint. And you know that the next one will be 7 house. And the next one you know for sure is going to be an 8. Hopefully you remember that it's rabbit. And then it goes reed, flint, house, rabbit. So the next one will be reed. And there it is. 9 reed, 10 flint, 11 house, 12 rabbit, 13 reed. So you know that the next one, the next year bearer will be 1. And if you guessed flint, you would be correct. 1 flint, 2 house, and then the next one will be 3 rabbit, 4 reed. The next one you should know it's 5 flint, and then 6 house, 7 rabbit, 8 reed, 9 flint, 10 house, 11 rabbit, 12 reed, 13 flint, 1 house, 2 rabbit, 3 reed, 4 flint, 5 house, 6 rabbit, 7 reed, 8 flint. Next one will be 9 house, you'll see. 9 house, 10 rabbit, 11 reed, and then 12 flint. There it is. 13 house, we're almost there. 1 rabbit, 2 reed, 3 flint, 4 house, 5 rabbit, 6 reed, 7 flint, 8 house, 9 rabbit, 10 reed, 11 flint, 12 house, 13 rabbit. And are you ready for this, you guys? Are you ready for this? After 13 rabbit, we have gone through 52 years. And then we get to 1 reed. There you have it. Then the whole cycle resets and we begin where we started. When you come back to the same position, you know you have gone through the whole thing. Now, this one, as you know, would be a very inexact calendar if you only accounted for 365 days. This system does not even acknowledge the fact that we have that little bit that is a little bit less than 6 hours extra in the revolution. And I love that I can talk to you about this concept and you understanding this. I hope hopefully you watched the whole lecture and now you're very well versed on these astronomical names. In the second part of the lecture, I will show you that we're still debating if they adjusted. We do know that the Aztecs observed the sun very closely. I mean, they worshiped the sun. I just showed you the sunstone, and when we look at the gods next week, they had a sun god. The sun is something that they watched all the time. And in the next portion, I will show how they had priests that all they would do is do these observations, and they actually had a lot of discussions about how to do adjustments. So they knew, just like the rest of the people in the world, they knew that they needed to cause some adjustments, because don't forget that a lot of times the calendar is made so that you know when to celebrate already. And there it is again, the Shiumolpili, the 52-year cycle. We just went through that. Why? Because I'm insane. And this is how the scribes depicted it for the Chronicle by Friar Diego Duran, one of my favorite. He's amazing. You should definitely read his books on the Aztecs. So here we have the reed year bearers, and here the rabbit, conejos is rabbit, cañas is reed, pedernales is flint, and casas is house. Actually, they have it plural here, but it's singular. It's just the word. It should be 1 house or house. That's the name of the year bearer. And the day sign too. Don't forget. Now let's look how Mesoamericans recorded Venus cycle. Before doing that, let me briefly explain a few astronomical concepts. First of all, Venus, as is Mercury, are interior or inferior planets, meaning their orbits are located between the Sun and the Earth's orbit. Consequently, their orbit around the Sun is smaller than that of the Earth, and also because of their proximity to the sun, they travel faster. Here are some astronomical cycles that include those of our moon, stars, and planets. I just listed a few here. So I'm just trying to show you the various orbits of important celestial bodies. For example, our moon, whose orbit is about 28 days, that's the average, but everything in astronomy is so complicated because you could count a sidereal month, which is about 27.32 days, or a synodic month, which averages about 29.53 days. The sun, we already went over. Mercury is about 88 days, and Venus about 225 days. However, Mesoamericans, including the Aztecs and the Maya, what they record in their manuscripts and architecture is Venus's synodic cycle. Is not Venus's orbit of 225 days, but Venus's synodic cycle, which is the time it takes Venus to go from one specific station to the next one from our vantage point on Earth. Typically, Venus's reckoning begins at inferior conjunction. So a Venus synodic cycle would be to go from inferior conjunction to the next inferior conjunction. And conjunction literally is multiple events occurring at the same time or at the same point. As you can see, conjunction in this context means that all of these three celestial bodies are lined up: the sun, Venus, and the Earth. And this is inferior conjunction because Venus is between the Earth and the sun. Also, inferior conjunction is a period of Venus invisibility. That means we cannot see Venus. It's there, but we cannot see it because of the bright sun. And then a few days later, you get to M first, which literally means morning first. As you can see, Venus's orbit is smaller than that of the Earth. Consequently, after Venus completes one of its orbits, the Earth is actually trying to catch up with it, because after the Earth has completed its orbit around the sun, Venus has already gone approximately through 1.5 of its own orbits. To get from one inferior conjunction to the next inferior conjunction, so to get to this point, again, that's the definition of a Venus synodic cycle. And the Venus synodic cycle is not 584 days, but 583.92 days. Let me go over Venus's phases or stations. So we have inferior conjunction, M first or morning first, greatest western elongation, M last or morning last, superior conjunction, E first or evening first, greatest eastern elongation, and E last or evening last. Inferior conjunction is when Venus is between the sun and the Earth, and superior conjunction is when Venus is on the other side of the sun, you see. So this is the Earth, this is the sun, and that's superior conjunction. At both of these junctures, Venus is invisible from our vantage point on Earth. And also M first, literally morning first, because you're looking or observing to the east in the morning. And then you have greatest western elongation. And elongation is angular distance. And that's because the sun is at the farthest away point from Venus. See? It's the time when Venus, as it appears in the morning sky, is the farthest away from the sun. And so that's why it's called greatest western elongation. And then around here, you have M last. And literally, we saw that M first, around here, is the first visibility of Venus as morning star. And then you have a day that is M last, or last visibility of Venus as the morning star. So from here, from M first to M last, Venus is visible. But at this juncture and at this one, it's invisible. And then we begin sighting, not in the morning, Venus won't be there. you have to observe Venus in the evening sky after superior conjunction. And then the sun is invisible. Excuse me. And then Venus is invisible. And then it will reach the point of E first, or evening first, the first visibility of Venus as evening star. And then it reaches greatest western elongation, again, when the angular distance between the sun and Venus is at its greatest. Then the Venus cycle continues until it reaches E last or evening last around here. And that is the last visibility of Venus as evening star. Then Venus begins a period of invisibility again. So therefore, you have two periods of invisibility around these conjunctions. And let me just say that at the greatest western elongation point is the first day when Venus reaches the highest elevation in the sky. And also, Venus is as far as it ever gets from the sun. And this point is also a period when Venus is visible for the longest period of time in the sky. And not surprisingly, is also the moment when Venus rises at the earliest time before sunrise. And I should say that all of the observations on this side, you would be looking towards the east and in the morning. What you see on M first is the fact that Venus, when you begin observing before dawn on M first, which is first visibility of Venus as morning star or heliacal rise, you will see that first Venus rises as morning star, and then the sun rises. Heliacal means near the sun or related to the sun. By the way, Venus is never too far away from the sun, so this point and this point are significant. And also, all the observation on this side, you would be looking towards the west and in the evening. Now we're ready to see how Mesoamericans recorded Venus cycles. It was often in bundles of 65, as you can see in this chart here. This is very similar to the 52-year cycle bundle. This one, the Xiomolpili that we studied earlier. And the 65 Venus cycles equal 2 sacred 52-year cycles, which is the same thing as 104 solar years, and also the same as 146 Tonalpowali, or the 260-day cycles. As you will recall, the year bearers that occur in the 365-day cycle are reed, flint, house, and rabbit. And not surprisingly, since it's the same exact system, something similar happens with Venus cycles. The initial days of the 584-day cycle are crocodile, serpent, water, reed, and motion. Motion is also translated as movement. Therefore, the first day of a 584-day cycle, the system that Nawa used for recording Venus synodic cycles, can begin on only these 5 of the 20-day signs of the Mesoamerican calendar. The relationship between 13 and 20 with 584 gives us the reason why these are the initial days, kind of like the year bearers, if you will, of the 584-day cycles. And that relationship between 584 with 13 and 20 refers obviously to the coefficients and the symbols too. And because 584 into 20, which is the number of symbols that the Mesoamerican calendar has, equals 29 with remainder 4, every initial day of every 584-day cycle will be 4 days from where the last one fell. So here I have rearranged the 20 symbols of the Mesoamerican calendar. As you can see earlier, for the solar year, I had them arranged so that reed was the number 1 symbol. So here I have placed crocodile as day sign number 1. So if this is 1, the next initial period of the 584-day cycle will be and I just told you the remainder was 4. So the symbol in every subsequent cycle will be 4 days from when this one happened. So this is 1, 2, 3, 4. So the next initial day sign will be serpent. And then 1, 2, 3, 4. That's the next initial day, which is water. And then 1, 2, 3, 4. That's the next initial day, which is reed. And then 1, 2, 3, 4. Movement will be the next initial day. And then we'll go back to 1, 2, 3, 4, crocodile. Another aspect of the 365-day and 584-day cycles is that whereas the coefficients in the 365-day cycle increases by 1, you will remember that it was 1 reed, 2 flint, 3 house, 4 rabbit, 5 reed, 6 flint, 7 house, and so on and so forth, increasing by a factor of 1. For the 584-day cycle, the reason why the coefficient would go from 1 to 13 or 12 to 11 is because of the mathematical relationship between 13, which is the number of coefficients in the Mesoamerican calendar, with 584. Because 584 divided by 13 equals 44. And it has a remainder of 12. So the coefficient in every subsequent cycle will be less than the last one by a factor of 1. So as you can see here, 13 serpent is 1 less than 1 crocodile because remember the coefficient or the numbers is only from 1 to 13. So the difference between 12 and 13 is 1. The difference between 10 and 11 is 1. So let's go over the cycle now. Let's see. If a 584-day cycle begins on 1 crocodile, so I put V1 as Venus 1, then 584 days later, the next one will be 13 serpent. Because, look, 13 times, let me show you. We have 13 times 1, 2, 3, 4, 5. 13 day signs times 5 is 65. So each column is 65 day signs. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 65 times 9 equals exactly 585 days. So 12 lizard will be the last day of the 584-day cycle that began in 1 crocodile. So then 13 serpent would be the 385th day, and consequently that is the coefficient for that second 584-day cycle. At the end of the 65 cycles here, I'll show you the chart again so it becomes clearer. So 1 crocodile, and then the next cycle would be 13 serpent, and look at the coefficient. It's not as straightforward as the 365-day one because it increases by a factor of 1. This one decreases by a factor of 1 because 13 before 13 is 1. So let's see the next cycle. So the next cycle, you can expect the coefficient to be 1 less than 13, so it would be 12. And try to remember the order, the initial period of the Venus cycles, which are crocodile, serpent, water, reed, and motion or movement. By the way, I put motion here because movement was a little bit too long for making this chart. It would mess it up. So consequently, you could expect the third Venus cycle to be 12 water. And there it is, 12 water. And the next one would be 11 reed. And there it is, 11 reed. And then the next one would be 1 less than 11, and it is 10 motion. So then the next one would be, we're going back to crocodile, so it would be 9 crocodile. And there it is. Then we have 8 serpent, exactly. And then the next one would be a 7, and it would be 7 water. And then 6 reed would be the 9th 584-day cycle. And after this, we would have a coefficient 5, and after reed would be movement. And there it is, 5 movement. And then we would expect a 4, and we're back to crocodile, so 4 crocodile. And then the next one would be a coefficient 3, and you know that serpent, the next initial period for Venus cycle. So Here it is, 3 serpent and then 2 water. The next one would be 1 reed, and there it is, 1 reed, and then 1 less. If we're only counting on coefficients 1 through 13, would be 13, wouldn't it? So then the next cycle would be 13 motion. And then the next one would be 12 crocodile, and then 11 serpent. The next one would be 10. And if you guess water, you would be correct, 10 water. And then the next one would be 9, and it's 9 reed. And then the next one would be 8. And after reed are the motion or movement. So 8 motion or 8 movement. And then 7 crocodile right here. And the next one, will be 6. And it would be serpent, of course. And that's 6 serpent. And then the next one would be 5. And then water. And there it is, 5 water. And then the next one would be 4. And if you guessed reed, that is correct. 4 reed, and then 3 motion. And then you always know that after motion, it's back to crocodile. And there it is, 2 crocodile. The next one would be 1 and serpent. 1 serpent. And then the next one would be 13 water. There it is. And then 12 reed. After reed, comes movement. So 11 movement. There it is. Next, we have a 10, and we're back to crocodile. So 10 crocodile. The next would be a 9 serpent. There it is. And then 8 water. After water comes reed. Always remember, the order is crocodile, serpent, water, reed, and movement. And I tried to say it so that you commit that to memory. So after 8 water, we will have 7 reed, of course. And there it is. After 7 reed, we have 6. And it would be motion. There it is, 6 motion. And then 5, and we're back to crocodile. 5 crocodile, 4 serpent. And then the next one would be 3 water. There it is, 3 water. And then 2 reed would be the next one, 2 reed. And you know that after reed, it's motion. So we would have 1 movement or 1 motion. There it is. And then we're back to the crocodile initial period. So 13 crocodile. And then we should expect a 12 and a serpent. So 12 serpent. After that, we have 11, right? So 11 water. And then after that, we would have 10 reed. And there it is, 10 reed, 9 motion. After 9 would be 8, of course. And we're back to crocodile. So 8 crocodile. After this, we'd have 7 snake or serpent, 7 serpent. After this, we would have 6 water. There it is, 6 water, and then 5 reed. The next one should be 4 movement. There it is, 4 motion. And the next one would be 3 crocodile. There it is. And then the next one, if you guessed 2 serpent, you would be correct. 2 serpent, 1 water. After that, it would be 13 reed, wouldn't it? There it is, 13 reed. And after that, it would be 12 motion or movement. There it is, 12 motion or movement. We're almost there. And then we would expect an 11 crocodile. There it is, 11 crocodile and 10 serpent. And then we would expect 9, and after serpent is water, because one last time, the order would be crocodile, serpent, water, reed, and motion or movement. The next one would be 9 water. And there it is, 9 water. The next one should be a reed year, and obviously the coefficient 8. So 8 reed. There it is. And then the next one would be 7 movement, wouldn't it? 7 movement, and then 6 crocodile. And then the next one should be a 5 serpent, of course. 5 serpent. And then the next one would be 4. And then the next JSON would have been water. So 4 water. There it is. And next would be a reed year, and obviously a 3. So 3 reed, and then 2 motion. And that's 65 Venus cycles, or cycles of 584 days each. And that's a count that is the same as 104 years or 52 year bundles. Okay. And then the amazing thing about the system in the Mesoamerican calendar is that after 65-day cycles, the whole system will reset, and we begin on 1 crocodile again. which is quite remarkable. And so we went from one crocodile to two movement. We went through 37,960 days. So like I wrote here, on whatever day we are on the Venus cycle, 104 years later, all of these cycles will coincide or reset. Now let me say a word about history, because the historic aspects that I'm about to tell you will help you to understand the Mesoamerican calendar better. In the 1880s, Ernst Forstemann stumbled upon the Dresden Codex, a Maya manuscript from the Postclassics, at the Dresden Library in Germany. And he began analyzing this manuscript and realized that pages 24 and 46 through 50 tabulate 2,920 days, which equal 584-day cycles and 365-day cycles running concurrently. Because 5 Venusian cycles and 8 solar cycles are exactly equal in number of days if you don't account for the difference of a little bit less than 6 hours for the sun. And as you can see here, the Venus synodic cycle is not 584 days, but it is 583.92 days. The other thing that Forstemann found was that these pages not only correlated these Venus and Sun cycles, it also distributed the 584 cycle into these periods, 236, 90, 250, and 8, which equals 584 days. Consequently, Forstemann realized that the Maya were not only recording Venus cycles, but that they were also indicating the different phases that we see in Venus cycles. For example, these two short periods of 90 and 8 are the periods of Venus invisibility at these conjunctions. Given all of this evidence, Forstemann called the information in these pages the Venus tables. Now, Forstemann was puzzled by page 24, which included numbers and symbols that he could not decipher. However, in the 1920s, another momentous event occurred when John Teeple, a chemical engineer, began studying the Venus tables in the Dresden Codex and discovered that page 24 actually features a formula to help adjust for the error that accumulates when Venus cycles are recorded as consisting of 584 days instead of 583.92 days. Teeple thus demonstrated that really complicated computations on this page actually indicates with certainty that the Maya understood that periodically adjustments had to be made to the calendar to reflect the real movements of these celestial bodies. These Maya studies have become indispensable in the study of the Mesoamerican calendar in general, including for central Mexico. For example, thanks to the studies of the Dresden Codex, scholars have been able to recognize that pages like these ones from the Codex Borgia, an Aztec or Eastern Nahua pre-contact manuscript, as you can see from the late post-classic. This detail is from page 53, and this is page 54. There's various other examples also in sculpture and other manuscripts as well. I just wanted to show you one example. Thanks to the studies since the 1880s of the Maya Dresden Codex, scholars of Central Mexican manuscripts have been able to use those findings to analyze the Venus cycles that Central Mexican manuscripts also recorded. For example, as you can see here, these are the initial periods of Venus cycles. See, they are featured in each of these 5 compartments. Look, see, we have 1 compartment, 2, 3, 4, and 5. And clearly, they are referencing the initial days of 584-day cycles, or Venus cycles, which, as you will remember, would be crocodile, serpent, water, reed, and movement. And here they are. You can see over here the crocodile initial periods, followed by the serpent initial periods. And then we have water, reed, and movement. Consequently, these are also Venus tables, similar to those in the Maya Dresden Codex. And even though scholars of Central Mexican manuscripts and other artworks have immensely benefited from the studies of the Dresden Codex, scholars have been unable to detect the very detailed data the Maya mathematicians and astronomers provided in the Dresden Codex. Nevertheless, just as studies of the Dresden Codex have informed the scholarship on Central Mexican artworks, Central Mexican ethnography and artworks have actually also been crucial in Maya studies. For example, even though this 8-day period was recorded in the Dresden Codex, it is from Aztec ethnography that we know what those 8-day period of invisibility entails. It is the Aztec creation accounts in Annals of Cuautitlan, for example, that we understand about the 8-day period of invisibility. Look at what the Aztecs say. Quote, the text says, the old people said he, Quetzalcoatl, was changed into the star that appears at dawn. Therefore, they say he came forth when Quetzalcoatl died, and they called him Lord of the Dawn. What they said is that when he died, he disappeared for 4 days. They said he went to the dead land then, and he spent 4 more days making darts for himself. So it was, after 8 days, that the morning star came out, which they said was Quetzalcoatl. It was then that he became Lord, they said. So just as the studies of the Dresden Codex have been crucial in Central Mexican studies, this bit of information has been essential in Maya studies as well. Because what this text is saying is that the iconography of Quetzalcoatl, or the Lord of Dawn, which is another word for Tlahuizcalpantecutli or Venus, alludes to the planet Venus. It's also talking about disappearances for 4 days and then an additional 4 more days for a total of 8-day period of disappearance or of invisibility. Okay, part 2, the new fire ceremony. In this folio from the Historia Tolteca Chichimeca, a manuscript from Cuautinchan in modern-day Puebla features a cave from where tribes are emerging. One of the many significant features is this image of a man wearing a headdress, an elaborate headdress, and boring a fire, and these glyphs evoke smoke, is signifying the conclusion of a 52-year cycle and the start of a new one. One of the most special celebrations among the Aztecs. It's called Binding of the Years. You will remember earlier in the lecture, I showed you the glyph for the new fire ceremony. Xiumopili is bundle of years, meaning that all of the years were tied up into one. And again, it was such a solemn celebration. Artists would receive commissions. It's commemorated in manuscripts, in stone sculptures such as this one, featuring 2 reed, which corresponds to the year 1507. So that's the closing of a bundle of years and the start of a new one. So the Aztecs would have celebrated the next one in 1559. And let's see what the Aztecs said in the Florentine Codex on Book 4 about this new fire ceremony. It's one of the most beautiful explanations that expresses the solemnity as well as the beauty of this new fire ceremony and the binding of years and how the whole community comes together. It says, the purpose or intention of this count is to renew every 52 years the covenant, contract, or vow to serve the idols. Because at the end of the 52-year cycle, they observed a very solemn feast and made new fire and extinguished all the old fires. And all the provinces of this new Spain took of this new fire. Then they renewed all the statues of the idols and all of their adornment, as well as the intention of serving them for the next 52 years. The longest time count, which they reckoned, was up to 104 years. And this count, they called a century. Half of this count, 52 years, they called a bundle of years. This period of years they had reckoned from times past. It is not known when it began. On the night of this feast, which they call Toshimopilia, the binding of the years, it so befell that the Pleiades were at the zenith at midnight, with respect to the horizon in Mexico. On this night they made new fire, and before they made it, they extinguished all the fires in all the provinces, town, and houses in all of this New Spain. So there is so much information in here. First of all, they're saying that the intention of this count was a renewal of a covenant to serve the gods, right? And the beauty of this is that it must have been such a gorgeous sight for them to extinguish all the old fires and ignite from a single fire a new fire from which everyone in the community would partake. It must have been a really stunning sight to see everything darkened and then a glow again from the fire coming from a single source. So you can see the sense of community in this celebration. And also, one thing that this text highlights as well is the focus on watching the movements of celestial bodies and the focus on the time of the day as well. And the text continues. All of the priests and servants of the temple departed from here, the temple of Mexico, during the first quarter of the night and went to the summit at midnight, or almost, where stood a great pyramid built for that ceremony. Having reached there, they looked at the Pleiades to see if they were at the zenith. And if they were not, they waited until they were. And when they saw that they now passed the zenith, they knew that the movement of the heavens had not ceased, and that the end of the world was not then, but that they would have another 52 years, assured that the world would not come to an end. At this hour, a great multitude of people was on the mountains surrounding this province of Mexico, Texcoco, Xochimilco, and Cuautitlan, waiting to see the new fire, which was a signal that the world would continue. And when the priests made the fire with great ceremony upon the pyramid on that mountain, then it was seen from all the surrounding mountains. Those who were watching then raised a cry, which rose to the heavens with joy that the world was not ending and that they had another 52 years assured. How beautiful this is, because it not only shows pageantry, but above all, it shows a sense of unity, a sense of community, and also a common belief. It shows so much sense of unity, not only physical, but also spiritual and philosophical, doesn't it? Because everybody was watching this event and everybody was expecting for the fire to be ignited, so that would give them the reassurance that life would continue and that the movements of the celestial bodies would continue. And the act of doing that would assure that another 52-year cycle would continue. And the beauty of the cycles in Mesoamerica is that when one ends, there's the promise that another one would begin. Thank you for watching. I hope you liked this. And these are the works cited. I found this image online in this article, by the way.